Hello, students. We are still in the revision lecture, and now we will review common discrete distributions, at least commonly encountered in actuarial studies, but elsewhere as well. So the first one is the Poisson distribution. Remember that we have this notation n tilde whatever means n follows the distribution written there. So for the Poisson, you know there's only one parameter, okay, which is lambda. So it's a simple enough discrete distribution. Of course, you know that a discrete distribution means that the possible values for the random variables are countable, okay, and in the case of the Poisson, the possible outcomes are all the non-negative integers 0, 1, 2, etc. Now, the probability mass function, obviously, this is just the probability that n takes a specific value, little x, is given by this expression, e to the minus lambda, lambda to the x, divided by x factorial. Now, what is the interpretation of the Poisson? At least one interpretation is that if you have a time interval and you're counting the number of events that are going to happen in this interval, if the rate at which events happen is constant over time, so it never changes over time, and if events all happen independently of each other, meaning if you know an event just happened, it doesn't change at all the prospect of another event happening later, this would also correspond formally to having the time between events being an exponential distribution, because the exponential has a memoryless property. So if all those assumptions are true, the number of events in any time period is going to be a Poisson random variable. And this, you can all prove this mathematically, but here I'm just reminding you of those facts. But regardless of this interpretation, the Poisson is very often encountered because it's simple. It has only one parameter. It has the property that the expected value is equal to the variance. So yeah, you will see it very often. Now, of course, because it only has one parameter, it's simple, but it's also rather inflexible, meaning its shape, you cannot alter the shape too much because there's only one parameter controlling the shape. Now, you've probably seen before. So here we have the illustration for lambda equals 1. Those are the probability masses. If lambda is relatively big, so as lambda increases, you will see that the Poisson gets a shape that is more and more symmetrical, okay, that resembles a sort of bell curve. Now here I present without proofs all the results about the MGF, PGF expectation and etc. Those things they're in the formula sheet for the exam, so I don't think you necessarily need to know them by memory. Although knowing them by memory maybe saves you a bit of time in the exam, that you don't have to flick through the formula sheet to find results. But I leave this up to you. You'll see that those things are in the formula sheet. So anyway, MGF, PGF, they're there. As I said, the expected value is just lambda. And you have that the variance is also lambda. So here, the Poisson is a case where expected value and variance are equal. If you want some practice, okay, maybe you have some spare time, you don't know what to do, you can entertain yourself by doing this thing. So I haven't included any details here, but if you derivate twice the MGF and you evaluate it at t equals 0, you know this will give you the second moment of n, the Poisson here, and you will get to this expression. And then, of course, using this, you can take the first moment minus the first moment to the square, and you get to the variance, which is just lambda. Now the binomial distribution. This one has a very straightforward interpretation. If n is a binomial, n would be counting the number of successes in n independent trial, where every trial can be either a success or a failure, and it would be a success with a fixed probability here, p. So here this discrete random variable then has two parameters: n, the number of trials, and p, the probability of success within one trial. I say success in quotation marks because a success really just means it depends on what the situation is. You can define a success however you like. You know, it's a bit grim, but maybe n is counting the number of people who have died in a given time period. If that's the case, you would define a success as somebody dying. Okay. Now here you have the PMF of the Poisson, so simply the probability n equals any specific value x. Now here, careful, the support would be the non-negative integers 0, 1, but up to n, right? Because obviously the maximum number of success out of n trials is n. You cannot have more successes than the total number of trials. And so here, remember, this is a shorthand notation for combination, right? So maybe you can just write it here to make sure we all agree that this is the combination of x in n, which is n factorial divided by x factorial n minus x factorial. And you remember the interpretation of this is how many ways can I select X object within N objects where all the objects are distinct, but I don't care about the ordering of those objects. So yeah, I imagine this is something you've seen before. And I don't know if I have anything else to say about the binomial. Here we have an illustration for n equals 20 and p equals 5%. You see here you probably know that the expected value of the binomial is just n times p. So here you have n times p is 1. So you see it's the same expectation as with the Poisson over there. And maybe one thing to say is that you see the shape here of the PMF of the Poisson. Visualize it in your mind, and then I go to the one for the binomial. They look relatively similar. And there's actually a result that says that indeed, if n is fairly big, but n times p is not big, then the Poisson and the binomial are pretty similar. You can approximate the binomial with the Poisson. Now, this is a bit vague what I just said. N needs to be big and n times p needs to be small. So you can formalize this mathematically, but I'm just saying you qualitatively this result. And other illustration, if you have n times p relatively big, and again, I'm being a bit imprecise here, but you get that the binomial looks more and more symmetrical, okay, with the bell-shaped form. And here again, you have results that I provide without proof. I hope you'll forgive me, but they're standard results about the MGF, the PGF. As we said, the expected value is just n times p. The second moment is here, and then from the second moment and the first moment you can easily find the variance, which is just n times p times 1 minus p. Okay, now we review the geometric distribution. So if n is a geometric, it only has one parameter, which again we call little p, which again you can see as a probability. Now we have the MGF here. But we'll understand the MGF, sorry, not the MGF, the PMF, if we remind ourselves of the classical interpretation of the geometric, which would be this. In a series of independent trials, how many failures are needed until the first success? So here you're counting how many failures until you get your first success. Now, careful that with this interpretation, you can have the geometric be 0, because in a series of independent trials, each with probability of success little p, if the first one is a success, well, then you have 0 failures until the first success, in which case you have that x, n equals 0. Now, what's the probability that this will happen? Well, it's simply p, because in a series of n trials, the probability the very first one is a success. If the probability of having success is p, well, will be p. So this works with the general formula here. Of course, if little x is 0, this disappears, and you have the probability that x equals 0 is p. But this is exactly the probability that the first trial is a success. Okay, and you can deduce the other probabilities in the same manner. Was the probability that n equals 1? Well, that would be the probability that the first trial is a failure, and then you have a success. Well, this happens with probability q times p, which is here. What's the probability that n equals 2? Well, this would be having 2 failures and then a success. This happens with probability q times p, which matches this with x equals 2. Okay, so hopefully that is simple enough. You have the illustration for the geometric here with just an illustration where we picked p equals 0.5. But here, the shape will always be like this, like decreasing, because of course, this is a decreasing function of little x. A bit of work for us or for you to do. Can you derive the MGF and PGF of a geometric? I encourage you to do it yourself at home or, well, wherever you happen to be while listening to this video, on the train or at the beach or in a coffee shop. But if you don't want to do it, or you've just done it and you want to check, let's review. It's simple enough. MGF, just recall what the definition is. We can write it here for your convenience. Would be the expected value of e to the tx. So then you compute this in the usual way. If it's a discrete random variable, you sum all the outcomes. Be careful, the outcomes for what? Well, for this thing inside the expected value. Okay, so here you would sum for all the values of e to the tk, where k goes from 0 to infinity, and then times the probability that the random variable x takes specifically the value k, and this is given here. Okay, this is the PMF of I'm sorry, I mixed my x and my n here, but let's stick with n because that's the notation. Here I meant expected value of e to the tn. Okay, so this will be the probability that n, the random variable we're dealing with, takes the value k. Okay, and then you realize that here you have something to the power k, here you have something to the power k. You can put those together, which then you have qe to the t to the k. And then look at this sum. It's a geometric, infinite geometric sum. So wonderful, you know very well how to compute this since probably high school. Now, if the ratio in the geometric progression is smaller than 1, you know that this simplifies nicely to just 1 over 1 minus the ratio. Okay, obviously, this condition is very important. You do need this thing to be smaller than 1. Otherwise, this sum doesn't converge, in which case the MGF doesn't exist. So this is an example of MGF existing, but only for a certain subset of values of t. Okay, that's simple enough, I hope. PGF, extremely similar. You write the definition of the PGF, which would be, well, I can write it here. Let's not be lazy. I need to, you know, earn my salary once in a while. So PGF is e to the, sorry, not e, but expected value of r to the n. Okay, so then what are the possible values of r to the n? Well, they're here. R to the k, where k will take all the possible values, 0, 1, 2, blah, blah, blah. And then again, you multiply this by the probability that n takes a specific value, k. And again, same trick. You can put everything to the power of k, and you use, again, your geometric sum of a geometric series, and you get this. Well, you get this, provided that the condition here is verified. Hopefully you agree with all those calculations. And then we can move on and present the next random variable, which is the negative binomial. By the way, did I skip something here? Yeah, I don't present the I haven't presented the moments of the geometric, but you know that the geometric is a special case of the negative binomial. So I guess here I'm going for efficiency. From the moments of the negative binomial, which are over there, you can deduce the moments of the geometric. I'm gonna make this clear in a second. But for now, let's just review the negative binomial. So this is a discrete random variable with two parameters, K and P. So we have P, as with the geometric, you can view it as a probability. Then we have this other parameter, K. Let's first recall the interpretation of a negative binomial. So this would be a random variable that counts in a series of independent trials how many failures are needed, but now to obtain K successes. And because of that, it's a generalization of the geometric. Indeed, the geometric is a special case of the negative binomial where K equals 1. But so more generally, we have this negative binomial that counts, okay, how many failures do I need to get the first K successes, where K can be 1, 2, etc., 3, etc. In fact, I haven't written it here, but maybe I should have. We mean here K, this parameter, can take values, at least in this version of the negative binomial presented here, can take values 1, 2, 3, etc. Now, in light of that, we have that the PMF is as given there. So the probability that my negative binomial is specifically X is given by this expression. Again, you have this is a combination of X in K plus X minus 1. Now, the possible values of the negative binomial are all the non-negative integers, 0, 1, 2, 3, 3, etc. You see, there's no upper bound there because there's no upper bound on how many failures are needed to get the first K successes. Meaning you could have, if you're very unlucky, you can have 1 billion failures in a row, or 2 billion, etc. Right? There's no upper bounds on how many failures you can get before you get your first K successes. Now I think we can understand this formula here intuitively, and I think here maybe there's a bit of value me explaining it. So and maybe here let's just give a numerical example. It's always easier to understand with a numerical example. So example, let's imagine here we have just K equals 2. And then I want to find the probability that N equals a specific number, but here again, let's give a specific example. Let's say I want to find probability that N equals 4. Okay, so little x would be 4 here. So here again, the interpretation is I want to find the probability that I have 4 failures before I get my first 2 successes. Now, how can this happen? You can visualize this as being 6 trials, right? Because I need 2 successes and I need 4 failures. So you can have your 6 trials here represented as, those spots. Now, first thing to realize is that I need 4 failures before I get my 2 successes. This means that the last trials need to be a success, right? Because if I had 2 successes here, for example, I wouldn't have, it wouldn't work. I wouldn't be able to have 4 failures before I have my 2 successes. Okay, and I mean, this situation would mean N equals 3, right? I have 3 fails before I have my 2 successes. So I do need the 6th one to be a success. But then realize that with this last trial, in this case, the 6th trial being a success, my other success can be anywhere, right? Meaning, if I have a success here, and then a failure, a failure, a failure, a failure, well, that corresponds to the situation N equals 4. Because indeed, yes, I have 4 failures, and then on the very 6th trial, I have my 2nd success. But that's not the only combination that yields N equals 4. Indeed, if I start with a failure, and then I have a success, and then I have a failure, why this is K? This is F, failure. Same thing, N equals 4. So then if I want the probability that n equals 4, well, I need to sum the probability of each individual case that yields n equals 4. Meaning I sum the probability of this plus the probability that, as before, I had a S here and then a failure here. I sum all the cases, but all those cases are the same probability. Of course, this specific case has probability here. P to the K. So in my example, P to the 2, I have 2 successes, and then I have X failures, 4 failures in this case. Now Q here is the probability of a failure. Okay, so Q is defined just by 1 minus P. Okay, probability of failure. But now how many of these cases I have? This is what is given here. So I'm summing this number of times the probability of a specific configuration. Okay, and this is what I want indeed, because I'm finding the number of ways, so the combinations of the number of ways where I have X failures in how many possible spots. Careful, it's K plus X minus 1. Well, yes, here, how many trials I have excluding the very last, because I know the very last needs to be my success. Well, I have then, in my example, 2 plus 4 minus 1, which is 5, but in general, this would be number of successes plus the number of failures minus 1. Hopefully that makes a little bit of sense. If not, maybe just pause the video and try to convince yourself that this formula is correct. It gives me the probability of exactly X of n being equal to X, little x. Again, this is probability of X failures before I get my first 2 or first K successes. And here, as we mentioned, the geometric is then the same thing as a negative binomial with K equals 1. And then we have a bit of illustrations for values picked more or less randomly here. P equals 0.5, K equals 2. You get this. It's pretty, asymmetrical. But then if K increases and you keep P constant, you're going to get something that's more symmetrical. If you kept increasing K here, you get something that's even more symmetrical, bell-shaped. Okay, and then again, we present standard results without proof. Hopefully you forgive me. The MGF is here, the PGF is here. We have the expectation. Now, we did not present the expectation for the geometric, but obviously we can recover it from this general expression. If for the negative binomial, you have the expected value being K times Q divided by P, well, of course, for the geometric, you just replace K by 1 and you get the expected value of your geometric. Second moment is here, and then the variance is here. One last comment is that we often call the variance of a, we often call the negative binomial over dispersed compared to the Poisson at least, which means that its variance is larger than its expectation. Recall, for the Poisson, the expectation exactly equals the variance. It's just lambda. But for the negative binomial, you have a variance that is bigger than the expectation. Whoops, I'm going too far. Well, yes, that's the case because look at this. That's the expected value, and that's the variance. Well, the variance is just the expected value divided by P. You see? Take the expected value, divide by P, you get the variance. But P is smaller than 1, so you divide by something smaller than 1, it's going to increase the quantity you had at first. And I believe that's it. This video is already long enough, so I'll stop here and I'll make a different video for the continuous distributions. So thanks for having followed. See you soon.